So you know, in STEM or in STEAM, we use the engineering design process. And the first step of the engineering design process is identify the problem. Sometimes problems can be global. Sometimes they can affect our school or our community. And sometimes they can be a little bit more personal. And so the problem for this project that we're about ready to start is a little bit more personal, and it's about roller coasters. Raise your hand if you like roller coasters. Yeah. My daughters would like to say the same, except they've never been on a roller coaster because I am one of those moms. You may know one of these moms, you might have one of these moms, but I'm one of those moms, and I'm terrified of my kids going on a roller coaster. The logical side of me knows that roller coasters are safe, that they have to go through certain standards, that there are safety precautions, but then you hear about that one case. The one case where somebody gets hurt or somebody falls off or something bad happens on a roller coaster. And I just can't get past that happening to my child the one time I let them on the roller coaster. So my problem for you guys that I need you to solve is I need you to work as your team and design and build a roller coaster that can be fun and have a thrill factor, but still be safe enough that I would feel comfortable letting my own children go on it, okay? So I want you on a piece of paper just to take a moment, and with your group, I want you to brainstorm some things that you might need in order to solve this problem. The engineering design process starts out with identifying a problem, some kind of problem or need that needs to be solved. And like I tell the kids, that problem can be something that's a global problem, it can be something that affects your community or your school, or it can be something that's more personal, that just affects a few people or one person. Constraints and requirements, what are you talking about? Like
How much money we have?
Yeah, how much money do we have to build it?
Well, we have to keep in mind like all the construction restrictions.
Yeah, so
what are you guys thinking?
Like what are we using? The speed of it, the height,
And like
What kind of speed would you want on a roller coaster?
for it to be fast, but not like that fast. That like it'll fall off.
Okay.
and
Yeah,
like,
that would be bad.
what we have to do that's gonna ride the roller coaster. And
Okay.
If we have to make a different part or something, and like what materials we need.
Okay. What else are you thinking?
What's riding the roller coaster?
Okay.
And like what's our
What kinds of things would you want to include on a roller coaster? Like if you're going to stand in line a long time for a roller coaster, what would you want to have on there?
Yeah, like
Lots of loops?
Bears, or like to go upside down or something.
Yeah. I walked around and talked to a bunch of groups, and you guys talked about a lot of different things that were going on. So I want to just touch with each group and get a couple of things that you guys were kind of thinking about. So what were some things that you guys were considering? Eston,
what thing is going down a roller coaster?
why would that be important?
Because then we might have to make changes to our roller coaster, like we might have to put up barriers or something to prevent it from falling out, or we might have to make the roller coaster more sturdy so it doesn't fall down.
Okay. What are you guys thinking? Chris,
What would be the restrictions on the roller coaster?
what do you mean by restrictions?
Like the dimensions of the roller coaster so we know how big to make it and the supplies we're going to be using to create it.
Okay, so some of the requirements or some of the limitations you might have. Okay, what are you guys thinking?
How high or how long it's going to be.
Okay, why would that be important?
Well, if there's going to be restrictions, we can't really go above the height limit, and if there's like a time limit, we can't go above or below.
Okay. Would you want really high?
Yeah,
Why?
because gravity will make it go faster.
Okay, and fast is good for a roller coaster? I don't know, I'm thinking slow is good for a roller coaster. So this is kind of the basic overall of what the roller coaster will generally be made out of and look like. I made this one 5 or 6 years ago, so it's been through a lot, but I think it's held up pretty well because I think structurally it's pretty sound. But some of the basic components and stuff are going to be things that you're going to want to include in your roller coaster. So this is not paper, it's actually paper cardstock, so it's a little bit harder than paper. Olivia, will you put the marble in for me? Now, I know funnels aren't really something that you would find on a roller coaster, but they are kind of fun. All right, you want to do it one more time so everybody can see? So it has a bunch of turns. It does have a loop where it goes upside down. And then it does end in a cup at the very bottom, which are all things that your roller coaster is going to need as well. So while you want to have things go fast and you want to have a lot of turns and things like that, at the very end, you do have to be able to slow down the roller coaster enough that the marble will go into a cup and not jump out of the cup. Definitely don't want that to happen. So in your binders, there are the project requirements and the outline for what you guys will need to make sure that you always check to make sure that you have in the final project, and the constraints. The requirements for the project are fairly broad. There's a base, and it has to fit on the size base. They can choose however wide they want as long as it fits on the base. The size is anywhere from 35 centimeters to 100 centimeters, which is a big range, and they need to decide what they want to do with that. And of course, the height definitely affects their energy, which would affect their speed and what they're able to do on the roller coaster. So that's a decision they have to make. They have a budget. And the thing I want to say about the budget is, because the kids are always surprised when I give them the amount. The amount is $65, and it's not the calculations with the money that are important in this project to me. It's knowing that money is a limitation at all, and will always be a limitation to any project. All right, so I'm sure you are wondering why I gave you candy when you walked in. Besides being an amazing teacher and that I like you, I do have a purpose for it. And by the end of the period today, I'm hoping that you will see or be able to explain how your candy and you eating the candy is able to power and light my flashlight. Okay? So we're going to talk about energy. And your candy is stored chemical energy. And there's two different types of energy. And in your binders, in the front is a sheet that looks like this. Go ahead and dig that out. We're going to keep referring to this today as we're reviewing energy. This is something that you guys should have already covered in your content science class, and so we're going to review it very quickly and make sure you guys understand it as we move forward. This is a science enrichment class, so we are here to support and extend and enrich whatever their physical science content is in their regular science content class. It is a semester long, so depending on when I get them first semester or second semester, it depends on what they've learned in their regular science because of the instructional calendar, which also may change from year to year. So sometimes I have to do more previewing, or they're learning it concurrently, and then other times they've already learned it and it's more of just a review. So usually I do like a pre-test at the beginning, and that kind of gives me an idea of how much background kind of research that I'm going to need to review with them, or whether they have a really good handle on the content already. We've gone over and reviewed some of the different types of energy, so let's see if you guys can tell me what type of energy is shown below. So in the picture. Eston, what type of energy?
Chemical energy.
What type of energy is shown below? Skylar.
Thermal energy.
Thermal energy. That would be heat. What types of energy? So this one has more than one. So think about what's going on in this picture. Ben, what do you think?
Mechanical energy.
Mechanical. What else, Patrick? Electrical.
I think Ms. Nations effectively uses project-based learning to teach the standards by allowing the kids to discover the AKS through the project. And what I mean is, she will look at all the standards that she has to cover, and then she is great about finding a lesson that incorporates every single one of the standards, so that kids are using multiple standards every time that they do something. They're not just isolating a standard in one setting. They're getting multiple experiences throughout that time. So she's really good at combining those things.
All right, so now what I want you to do is, as a group, I want you to brainstorm, and I want you to think about all the energy transformations that are going on between eating the candy, okay, and what's going on with eating the candy and it, you swallowing it and becoming stored chemical energy, to being able to then wind up the flashlight, and what else going on inside in order to be able to convert it to light at the end. okay? You can eat your candy while you guys are discussing this as a group, and I'm gonna come around and kind of see where you are. There are a lot of transformations going on. See if you guys can get them all.
All right. So the first thing is there's chemical energy stored inside this delicious piece of candy I made. That, and when we're chewing it, we're using mechanical energy to actually chew it. And then we're using gravitational energy to get it down our esophagus. Esophagus.
What is it?
Esophagus or throat.
What energy?
Gravitational to get it down our throat.
Then what?
We use the energy, potential energy we got from the candy and turn it into motion energy.
Or it can be sound when you chew it.
Yeah, and sound when we chew it.
That was good.
And then it turns into mechanical energy when we're turning it.
All right, what are you guys getting?
We have mechanical and chemical, thermal, gravitational, electrical.
What does it start out at though?
Mechanical.
Sitting in the thing right now, which is chemical.
So chemical, I put dissolved because like
But it starts out as chemical right now in the package. And then what?
then it eats. Then we eat it because
Okay.
we're chewing it, and
Okay.
then like I would think like thermal maybe because like it's like your mouth is like melting it.
Okay, possibly.
So then gravitational because like moving down, right?
Okay.
And then sound, we're chewing it, and electromagnetic.
So it's gravitational, which is potential, before it moves down. Then what happens?
Potential. It's like
Before, and then it actually does the movement, which is then,
kinetic.
yeah.
Oh.
See how there's lots and lots of steps when you think about it. A lot of times with questions, when I get different answers, a lot of times I try to ask other questions that might either scaffold and help lead them a little bit toward where I want them to go with it, or sometimes I just bring up other questions of other examples that make them think about why where they're going isn't the right direction. And when you bring up something maybe that counters what they're thinking, it does give them, time to pause, and they think, oh, and you don't have to actually tell them anything because they realize that they're headed in the wrong direction. A lot of times with this class, sometimes going in the wrong direction is okay because you learn a lot from that. And when you've gone that way and you've spent and committed some time, you tend to remember those experiences and what maybe you could have done in order to change it for the next time. So about the roller coaster itself.
Well, I thought the roller coaster.
It's
$60 to build.
it's pretty structurally very well because it's all very well supported, and basically the structure is very supported. Everything has a place where it's supposed to be. Nothing's really hanging. It looks too much.
Do you guys agree with all that?
Yes.
Safety, it's pretty decent. There's always one
And all
freak
these
bizarre,
parts are useful. It's not just there for nothing.
and there's every once in a while there is a freak bizarre accident. So give it a 4.
Like where?
Like right here on this drop right here?
No,
kinda
when it comes out, the marble doesn't always fall in the cup, basically.
Ooh.
Yeah,
Would that be a
that's,
concern?
No, it's not really a concern.
What does the marble represent? But what does the marble represent?
people.
So is that a concern that sometimes it doesn't fall in the cup?
But look, as it
The gallery walk is just another opportunity to give the students a way of kind of getting some ideas for brainstorming, starting to really look at the factors that are important, in terms of the structure, the way they laid things out, the height, the size, where they put different components, whether it would be fun or not fun, or what kind of speeds and different, just how the components work together. I think sometimes it's harder for students to visualize the 3D form version versus what they kind of see as, you know, their 2D ideas in their head. So it's just a way to, you know, get them talking and being able to start really thinking and discussing and collaborating as a group on what they want to do as they get ready to build theirs.
There's been a lot of things that I've learned that's new, but what I've learned most from this class is working with other people and using hands-on projects to help me in the future.
Miss Nation's class is different in the ways that you get to work with a group and you get to work with your hands more. And so basically, like, we explain, like, we learn about what we need to learn about it, and then we put it over into, like, real situations. So we actually know what's going to happen and not, like, just PowerPoints and stuff where we just see it happen on a PowerPoint and it just really doesn't look that real or anything. We get to test ourselves, and then we get to work with a group so that if we can't figure it out by ourselves, somebody else who might know something more about it, they help us with them and we help them.
They spent $61.22, but they were able to make 2 tracks.
See, they're cheaters.
Okay, you know what?
So the groups within the constraints and the criteria really have a lot of choice in what they can do, and they make their decisions. Their first decision when they get their design finished is they need to decide with the structure of the columns and beams how much they want to purchase outright, because there is a discount for the very first purchase of those. That would be a bulk order in real life, and that would happen. And so they would need to consider the fact that you don't want too much, but you don't want too little. And if you get too much, you can't return it and get your money back, and so you wasted a lot of money. If you get too little, I mean, in real life, you don't just keep ordering, you know, 2 columns here, 2 columns there. You would have to plan it out and do a bulk order. And then as they need parts or whatever, they can come and get them from the roller coaster store at any time. They just always have to come with their accounting sheet and make sure they account for anything that they purchase. The sheet tells how much everything is, and they need to subtract it. And they know that they're accountable for the sheet at any time. I can spot check it, and if it's not correct at that time, they lose points, because, you know, any kind of project manager or engineer that doesn't take care of money isn't going to last very long.
The test and evaluate part of the engineering design process helped me the most in my project, because once we tested it maybe 4 or 5 times, we really got to know the issues that we had with the roller coaster, and we evaluated the issues that we had and we fixed it. When our ball was rolling down the hill, it was going too fast. It had too much momentum when it was going around the curve. So what we decided to do, we decided to make the curve longer. Instead of like a short turn, we made it longer, so it was able to stop the momentum of the ball and make it slow down.
I learned a lot about how to design things safely, but you also have to make them fun enough so people are still going to want to ride them and stuff. But also you got to make sure, like, you got to have certain things that aren't going to test the boundaries of roller coasters, and you want to just overall just make sure they're safe for everyone and everybody enjoys them.
It's not gonna work. Well, we can test it. Where's the marble? Alright, let's test it, guys. Where's the marble? What are you doing? Alright.
Okay.
He's gonna finish that one.
Okay. All right. What are you guys adding? Do you see this though?
Yeah, no, we noticed that earlier.
So thoughts on how you guys can fix that?
Oh, we can put like a nurse support right here.
I don't think I mean, it does need a support.
Because it's just hanging in the air, and I'm going to tell you now, there's no way, no, my family's not going on it, I'm not going on it. So just put it down like right here. Just put it in the, yeah. Yeah, see how the whole track is moving a lot?
It needs support.
That's an issue, yeah.
Project-based learning can be very scary for a lot of teachers because of the fact that they don't feel like they'll have enough time. Projects take time. Teaching standards takes time. And when you've got a certain amount of standards you have to get through, and you've got an assessment, a common assessment, and in Gwinnett it's a common assessment that everybody's going to take, and you know you're accountable for that, it does make it hard. I think the biggest thing I can tell teachers is give it a try, go visit somebody that does make it work, and find out what happens.
The presentation day, it's more of kind of like a gallery walk. We have the roller coasters out, the thinglings are up, and then they kind of have a rating sheet, and the students walk around in groups and they look at the roller coasters and they kind of look at, judge the structure and the stability of it and the safety of the track and the fun factor, because sometimes things can be really safe and structurally sound but really not that fun. And then also look at the cost and the cost they would get from looking at the presentation.
Yeah, plus it's not even really connected, it just does this.
Yeah, so that's not very secure or structurally sound. I agree.
I give it a 3 out of 5 on safety.
No, I'm thinking 2 maybe. No.
So a lot of people have kind of mentioned this with the wobbly and stuff. What are your thoughts on that?
4 out of 5. I mean, nothing's falling down.
Yeah,
They could have made more of these stabilizers because there's none there.
Yeah,
Okay.
look, this entire part right here has no stabilizers.
Okay.
And these things are just kind of floating.
Yeah.
What are your thoughts on the fact that there's nothing right here at all?
It makes
I'm
it very...
thinking that it's going to be very easy for a natural disaster to destroy it.
What are your thoughts, Chris?
I think that it seems like they spent a lot of money and that they didn't have enough money in the end to create something like here. If they had, and it probably would have been much more secure. It seems like they could have secured the supports to the ground better.
Okay, so you think maybe they should have spent a little bit more of their money on supports and not so much on some of this extra track stuff? Okay.
Cheap though.
Yeah,
Okay.
So 2 out of 5.
Have you looked to see how much money they did spend?
Yeah, $61.22.
Okay, so they spent almost all of it.
Yeah.
Okay.
It can be hard content. When you mention science and math and technology and engineering, for some students that can be scary. But once they get in the classroom and they see that she's going to guide them, she's going to support them, and she's going to let them try, and if they fail, it's okay. And I think once they learn that that safety net's there and it's okay to try and not really fail, she more, I think, redirects them to say, well, what if you tried this? Or what if you do it this way? So it just makes them change their thinking.
I think it's so much more than just the science and the math. I think really any day that you can get students that are collaborating, communicating, that are problem solving, that are being creative, and they're taking some risks and trying new things, I think that's a successful day. And I think if they're having fun while they're doing it, I think not just successful, I think it's an amazing day.